Hello from Ozu Rover team, representing Özyeğin University in Istanbul, Turkey. We are proud to introduce our latest generation rover, RS4. Ozu Rover team was founded in November 2014 by undergrad students with the aim of creating a hands-on engineering environment. Our team brings together students from different academic backgrounds, and we are driven by a collective passion for robotics and space. To manage the development of the rover efficiently, our team is organized into several sub-teams. Each sub-team is led by a sub-team leader, and all sub-teams work under the coordination of the student team leader and their faculty advisor. This organizational structure allows us to divide responsibilities clearly while keeping all systems integrated as one complete rover platform. Ozu Rover team has been participating in the European Rover Challenge since 2015, and each year the competition has provided us with valuable technical and personal experience. For us, ERC is more than a competition. It's an opportunity to test the systems we develop during the year, improve our engineering skills, and gain real-life project experience under realistic field conditions. We want to participate in ERC because it pushes us to solve complex engineering problems, work as a coordinated team, and compare our solutions with international rover teams. With RS4, our goal is to present Özyeğin University and Turkey once again while continuing to improve ourselves as a future engineers.
As the mechanical sub-team, our primary goal this year was to improve our rover's operational durability and structural reliability. For our new locomotion system, we are building a sturdy yet lightweight framework combining carbon fiber tubes with custom CNC machined aluminum links. For our new BLDC motors, we optimized track width and wheelbase to improve lateral stability during skid steering maneuvers. The rocker buggy suspension allows all four wheels to maintain constant ground contact, ensuring high grip on challenging terrain. With this new iteration, RS4 stands 1.4 meters tall, 0.9 meters wide, and 1.2 meters long. The main chassis preserves topology-optimized design, manufactured from 2mm laser-cut galvan steel. To minimize flexing caused by the locomotion axles, we integrated a fixed transverse reinforcement shaft between the side frames, while adding two supporting beams to the arm base for extra rigidity. Our wheel assembly integrates 3D printed ABS rims, which is specifically chosen for its outdoor durability, and flexible TPU tires. Honeycomb infill provides essential passive damping, while the curved profile and fuzzy skin surface optimize traction. The 5D Exofreedom robotic arm features a carbon fiber and aluminum hybrid structure, achieving maximum rigidity at a minimal weight. Each joint is driven by CubeMars AK60 brushless DC actuator and anti-backlash worm gear reducer, which enables self-locking capability, allowing the arm to maintain payloads over 6 kg and reach up to 1.5 meters with zero power draw. Finally, for the end effector, we implemented a dual lead screw mechanism for precise parallel clamping. With its interchangeable fingers, the griffle can handle everything from maintenance tasks to soil collecting. We also utilized a slip ring for continuous 360-degree rotation and repositioned the camera to eliminate any potential blind spots.
As electrical electronics sub-team, we custom engineered two power boards to reliably support our rover's critical operations. Our primary board delivers up to 90 watts to run NVIDIA Jetson AGX Orient at peak performance. To ensure maximum stability for this sensitive electronics, we utilized a synchronous buck converter topology. Through extensive simulations and real-world testing, we achieved a 93% efficiency rate at maximum load and reduced peak-to-peak performance to just 0.4%, well below the industry standard. For system safety and battery monitoring, we integrated hardware-level under-voltage protections directly into our power board and motor controllers. This architectural upgrade allowed us to remove the old automotive relay, completely eliminating its excessive heat generation and resistive losses. Furthermore, we designed custom power distribution boards featuring resistable fuses, TVs, diodes for each motor. To safely clamp unwanted inductive voltage spikes, we also made a massive upgrade on our drive network by migrating to the EtherCAT protocol by connecting our four locomotion actuators in a daisy chain topology. We achieved deterministic real-time performance with a 1 millisecond cycle time. This provides low latency feedback we needed for challenging terrains. For the robotic arm, we retained our highly reliable CAN bus architecture. We utilized galvanically isolated transceivers to protect the O-ring from transient voltage spikes during rapid manipulator movements. For our primary base station communication, we engineered a robust point-to-point wireless bridge operating on 2.4 GHz band by pairing an industrial-grade MikroTik Metal 52AC on the rover with CP-Link CPE 210 at the ground station. We secured a high bandwidth, low latency link. With this setup ensures uninterrupted telemetry, real-time video transmission from the Jetson Orient, even across challenging high-interference environments. Finally, to enhance the rover's environmental awareness, we integrate the lightweight modular panel system, driven by two servo motors and a mounted on rigid sigma profile structure. It provides 360-degree camera rotation and a precise tilt control, maximizing our operational field of view.
For command and control, Our operators pilot the rover using a custom web-based graphical user interface, communicating via low-latency latency WebSockets. We also designed a context-aware bandwidth management system. This software intelligently monitors the rover's kinematic state and dynamically prioritizes specific video streams, such as automatically maximizing the rear camera feed when the rover shifts into reverse. This ensures optimal radio link usage without sacrificing the operator's situational awareness. Additionally, to enhance our manipulation and task execution, we have developed a custom inverse kinematics engine. This tool allows operators to visualize, calculate, and preview complex robotic arm trajectories in real time before executing them on the physical hardware, ensuring precise and collision-free operations.
Our autonomous navigation stack relies on Z2 stereo camera to convert 3D point clouds into real-time 2D occupancy grid. A custom path planning algorithm evaluates this grid sector averages to identify traversable terrain and actively avoid obstacles. By fusing GPS telemetry with visual tracking, the rover accurately navigates to waypoints and executes systematic search patterns to locate hidden AutoCode markers. Crucially, this entire reactive autonomy stack is being trained and validated inside our Unity simulation environment before field deployment. Finally, a software-level e-stop is continuously active, ready to instantly break the motors for immediate operator override.
As a science team this year, we focused on improving the reliability and the performance of our module for the mission. A science module weighs 6 kilograms and measures 260 to 230 at 650 millimeters. It covers deep sampling, surface sampling, on-site measurement, and astrobiology. For deep sampling, just as last year, our deep sample assembly has a drill attached to a DC motor, and another DC motor controls the vertical movement of the drilling assembly. This year, we made the system more reliable. It can collect samples from a depth of 30 centimeters on Martian-like soil, and our closed container system, which is also equipped with the load cell, minimizes material loss during the soil transportation process, ensuring more efficient and reliable sample collection. For surface sampling, we use a robotic arm to collect material directly from the surface, allowing us to collect both regolith and rocks. For the astrobiology task, we have mounted a pH sensor on the robotic arm, allowing us to measure both soil pH directly on site. Our module is also equipped with sensors that monitor air quality, ozone, carbon dioxide, and carbon monoxide concentrations. Additionally, it can measure humidity, soil moisture, temperature, and light levels, which can provide insight into the presence of potential water sources. Finally, for sample analysis, we use a Bradford assay with Kumasi brilliant blue, which undergoes a shift and absorption spectrum from 470 nanometers to 595 nanometers upon binding to proteins. A CCD spectrophotometer enables us to capture full absorption spectrum and convert absorbance data into graphical representation, facilitating precise analysis and interpretation.
For the drone exam test, our drone utilizes IMAX 980 kV brushless motors, 9-inch propellers, and a modified F450 chassis equipped with a protective outer cage. The flight stabilization is managed by an RW11Q point flight controller, paired with a Raspberry Pi companion computer for onboard edge processing. GPS is used for absolute positioning in order to establish a stable hover. Real-time data monitoring is maintained via 915 MHz telemetry module, while Raspberry Pi 4 is connected to the computer via 2.4 GHz Wi-Fi. High-level decision commands are sent to the Q-point over a physical wired serial connection utilizing the Melvin communication protocol. For the mission, required commands and algorithms for the precise landing and searching the area for finding the landing spot and the props are modeled and deployed within a MATLAB and Simulink framework. This complete control stack was verified in a gazebo simulation environment before the physical real-world flight test for preventing further accidents. The system sends deterministic modeling commands to guide the drone smoothly across all spatial axes, accurately controlling in order to up, down, right, left, front, and back, and of course for the landing. For the autonomous precise landing, a downwards facing Raspberry Pi Module 3 wide camera tracks the orthogonal marker of landing spot. The mission data is fused with a specialized TT mini lidar rangefinder. MATLAB algorithms process the spatial offsets in real time by applying velocity corrections against the feedback errors to execute a centered touchdown with under 5 cm of physical deviation. Prior to target acquisition, an Archimedean search algorithm governs the trajectory of the area scanning in motion. If an unexpected data link timeout or transmitter signal loss occurs, a routing safety protocol instantly starts an emergency auto land. It can also be initiated manually.